Hi dear, so welcome back to a new video. In today's video, we are going to see about factors which influencing the solubility. Here only the what factors is altering the solubility, whether the solubility will decrease or solubility will increase, will come to know by this factors. Okay, so we have here 7 factors. The factor 1 is temperature, second nature of the solvent, third the particle size, and the fourth one crystal structure and its polymorphism, fifth one molecular structure, sixth one is the pH, and eighth one common ion effect. So these 7 factors, how it influencing the solubility we will see, and it is very important portion for 10 marks. So now we will start with the temperature. Okay, so usually when we are increasing the temperature, yeah, we can tell the solubility is increasing, right? In daily life, when we prepare the tea, we'll use the sugar, right? So sugar will dissolve easily in the hot water, so we all know that. Okay, so the dissolution or the solubility is majorly depends upon whether your reaction is endothermic or exothermic. Okay, this is the first point which you have to remember. Okay, so it depends upon the dissolution, and if it is endothermic means will tell if it is absorbing heat. In the case of exothermic, if it is releasing the heat, we will tell it is exothermic reaction. Okay, so in the case of endothermic reaction, so the temperature will increases, okay, as well as the solubility will increases. So you can example the sugar solution as an example. In cold water, sugar will take time to get dissolved, but as if you are taking the hot water, the sugar will dissolve easily. Okay, so same here, potassium nitrate will increases the solubility by increasing the temperature. Okay, this we can give as an example. What? Potassium nitrate is an example of endothermic. Okay, in that when we will increase the temperature, solubility will get increases. The next one is the exothermic. In the case of exothermic, the temperature will increases, but the solubility will get decreases. So you can give the example like calcium hydroxide. Okay, so overall in the temperature case, you have to remember the Van Hoff equation. Okay, so Van Hoff equation, in that you can tell this is in ln will represent as ln S is for solubility, and ln S is equal to minus delta H by RT plus C, where delta H is the heat of solution, R is the gas constant, T is the temperature, and C is the constant. So when we will discuss the Van Hoff's equation, which relates to the change in equilibrium constant of a reaction to change its temperature. How the shift is taking place. If we can say like, if you change the temperature, how the reaction is getting shift, that will tells by the Van Hoff equation. So when we will discuss about the temperature, you must have to write the Van Hoff equation as well as the graph which is showing the temperature. So I will give in the graph in the video section, okay, that you can see. Now we will see the nature of the solvent. In the case of nature of the solvent, we know solubilities depends upon the similarity between the solute and solvent. Okay, so the principle of like dissolves like, right? Like dissolves like, we know only the polar solute will get dissolved in only in the polar solvent. In such like non-polar solute will dissolve in the non-polar solvents. So here you can see polar solvents such as water will dissolve polar or ionic drugs. So you can give the example of sodium chloride and paracetamol. Here the paracetamol is ionizable drug. Okay, paracetamol is the ionizable drug. And case of non-polar solvents like benzene, chloroforms will dissolve in the non-polar drugs. The non-polar drugs like oils are steroids. Okay. So when we will discuss about the nature of the solvent, you must have to remember the principle of like dissolves like. Like dissolves like means polar solute will only get dissolved in the polar solvent. Non-polar solute will get only dissolved in the non-polar solvent. If you remember the nature of the solvent, you can write. So that's all for the nature of the solvent. Now we'll go for the particle size reduction. Here you will see the particle size. We all knows if the particle size is less, it will dissolve easier, right? If its particle size is big, it will take time to dissolve, right? So here also the same thing. Here if we will reduce the particle size, surface area will get increased. Okay, if the surface area, if we will get more, usually the solubility will get increased. The concept is, if we are reducing the particle size, surface area will get increased. So thereby we will get the solubility also increased. So this concept is explained by Noyes-Whitney equation. How the surface area and particles reduction is affecting the solubility. So dC by dt, which is equal to dA into Cs minus C by H, where dC by dt is the rate of dissolution, how fast the process is taking place. Then D, diffusion coefficient of the drug molecules. A is the surface area of the drug. Cs is the concentration gradients, and H is the thickness of the diffusion layer. And the example for the particle size reduction, if we are taking the micronized means we will convert the particle into the micrometer range. So the micronized griseofulvin dissolves much faster than the normal powder. Okay, what? Micronized griseofulvin dissolves much faster than the normal powder. So we have to keep it in mind. If the particle size is less, we'll get the faster dissolution. It is explained by the Noyes-Whitney equation. I hope you people understood. Now we'll go for the next one, is the crystal structure and polymorphism. Here we'll see the crystal structure and polymorphism. We already know our drugs which will be either in the crystalline form or amorphous form. So when we will talk about the crystal structure, when two or more crystalline forms will join to form the polymorphs. Okay, so the process of formation of polymorphs will be called as polymorphism. Okay, so we can remember each form has the different solubility. When we are taking the crystal structure, each crystal is having the different parameters, like it will show the different solubility, maybe due to shape, or maybe due to polarity, maybe due to the molecular weight, anything may be the reason. Okay, so for example, amorphous penicillin G have more solubility than the crystalline penicillin G. So we can see the amorphous penicillin G. Amorphous means already your drug is in the loosely packed. If it is loosely packed means your molecules is, it will be, distance will be there between the molecules. So the energy required to break it is less. So we can conclude there the amorphous penicillin G have the more solubility than the crystalline penicillin G, because if it is in the case of crystalline forms, your molecules will be tightly packed. You can see here the molecules is tightly packed. So the energy required to break that molecule is more, right? So in that case, we'll get the reduced solubility. So we can, instead of the crystalline form, we can go for the amorphous form of the drug. So you can give the penicillin as an example. Next one is the chloramphenicol palmitate. What? Chloramphenicol palmitate. It having the two forms here. One is the form A and one is the form B. And you know, stable polymers and metastable, right? The stable polymers are showing the low solubility and metastable polymers will show the high solubility. Okay. So, this is the concept of crystal structure and the polymorphism. You just have to remember about the loosely packed molecules will be amorphous and crystalline case the particles will be tightly packed. Tightly packed means energy required to break is more. Okay, now we will see the next one, molecular structure. When we are talking about molecular structure, okay, so the structure of a molecule will determine the hydrogen bonding, okay, and the polarity and functional group and molecular weight. What? This a structure of the molecule will determine these things. What? Hydrogen bonding, polarity, functional groups and molecular weight. Okay, this thing which will influence the solubility. How? You can give an example of salicylic acid is more soluble than the benzene. How? Because adding a hydroxyl group or carboxyl group will increases the hydrogen bonding. If the hydrogen bonding is increases, okay, gradually the solubility also will increase. So next case, increasing the alkyl chain length. If you are increasing the alkyl chain length, which leads to the increasing hydrophobicity. If the hydrophobicity is increased, means what? Solubility gradually it will reduce. Okay, this is the concept of the molecular structure. You have to remember each structure of the molecule will determine it will give the hydrogen bonding, polarity, functional group, molecular weight. And you can give example of salicylic acid is more soluble than the benzene. Why? Because in that additional hydroxyl means hydrogen bonding is there. That is what? Addition of hydroxyl or carboxyl group which will increases the hydrogen bonding. If the hydrogen bonding is more, the solubility will increase. Next case, increasing the alkyl chain length. If the alkyl chain length we are increasing, gradually it will lead to the increasing hydrophobicity. If the hydrophobicity is increasing, means gradually the solubility will decreases. Okay, so now next concept we will see the pH, how it's affecting the solubility. The pH is only for the ionizable drug, those drugs which can ionize. Okay, so this pH will affect the solubility of weak acid as well as the weak bases. What? pH will affect the solubility of weak acids as well as weak bases. So it is given by the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. So for a weak acids, we can represent the solubility is equal to S naught into 1 plus 10 raised to pH minus pKa. Okay, in the case of it is for weak bases, it is S is equal to S naught into 1 plus 10 raised to pKa minus pH. Okay, so here S is for solubility and S naught is for intrinsic solubility. Okay, so if you are taking in the case of weak acids, solubility will increases at high pH. So in the case of weak acid, if you are taking the weak acid, the solubility will increase in the high pH. If you are taking a weak base, solubility will increases at low pH. Okay, so if you are taking low bases, we have to maintain the low pH to get the solubility or to increase the solubility. Okay, so you can take aspirin as the example. So aspirin, we know aspirin is the weak acid. So that weak acid, when we dissolves more in the intestine, why? Because intestine pH is 6 to 7, right? So then in stomach, so stomach pH is usually 1.2. It is near about 1.2. So it is too less. We want higher pH. So the aspirin weak acid will dissolve more in the intestine pH, that is 6 to 7, than in stomach. Okay, understood? What? It's for the concept here which you had to remember. This pH is for ionizable drug. In that case, the pH only will affect the solubility of weak acid as well as weak bases. And you had to remember the Henderson-Hasselbalch equation for your weak acids as well as for weak bases. Okay. So, here how the technique is there to remember. S is equal to S naught 1 plus 10. It will same. Then pH minus pK is in the case of weak acid. But in the case of weak bases, it is like pKa minus pH. Okay. Then you have to remember this point. Like weak acids, in the case of weak acid, if you want increasing the solubility, it will show in the higher pH. If in the weak bases, solubility will increases only at low pH. Okay. I hope you people understood. Now we'll go for the last one, that is common ion effect. Yeah. In the case of common ion effect, we can see it occurs when a dissolved salt releases an ion that is already present in the solution. Okay, so you have a solution here. Okay, so in the solution already some ion is present. Okay, okay, and you are adding a salt. Okay, so if that salt is releasing a same ion which is present in the solution, which will decreases the solubility. What is the concept? You have already the solution. Solution is containing the particular ion. Okay. And you are adding the salt into your solution. And if that salt is releasing a same ion which is present in your solution, which will decreases the solubility. Okay. So you can see adding common ions will reduces the solubility of weak electrolytes. For example, solubility of AgCl will decreases if NaCl is added. Here, common ion is the chloride. What? Solubility of AgCl will decreases if NaCl is added. Here we have the chloride. And next case, benzoic acid solubility will decreases when you are adding the sodium benzoate. So the common ion is benzoin. This is what common ion effect. Common ion effect means adding common ions will reduces the solubility of weak electrolytes. The concept is like you have the solution and in the solution ion is present, and if you add the salt, if that salt is releasing the same ion which already present in your solution, it will decreases the solubility. This is what common ion effect in solubility. Okay, so now we had completed the 7 factors also. I hope you people understood. Okay, so in a short we will go this 7 parameters once again. So the temperature is depends upon the dissolution is endothermic as well as exothermic. If it is endothermic means energy absorbing process, exothermic means energy releasing process. So in the endothermic reactions, the solubility will get faster. If you increase the temperature, solubility will get faster. In the case of exothermic reaction, if we increase the temperature, solubility will get reduced. The example you can remember KNO3 and calcium hydroxide. Okay. Then nature of the solvent. In the case of nature of the solvent, you have to remember the principle of like dissolve like. That means polar solute will only get dissolved in the polar solvents and non-polar solutes will get dissolved in the only non-polar solvent. And when we are discussing about the particle size reduction, if we are reducing the particle size, the surface area will get more. If the surface area is higher, you will get the increasing the solubility. Okay. Next one is the crystal structure and polymorphism. So we have amorphous as well as crystalline form. So this polymorphism is nothing but two or more crystalline forms joined together and it will form the polymorphs. So the formation of polymorphs will be called as polymorphism. Okay. So in that your molecules is tightly packed. So in the crystal, if it is a crystalline, it will take time to get dissolved. So solubility will be reduced, solubility will be decreases. And if amorphous, your molecules is loosely packed, so energy required to break is less, so solubility is higher. Next one, the molecular structure. So molecular structures will give the hydrogen bonding, polarity and all, right? So the molecular structure will also determines the solubility. And in the case of pH, it's only for the ionizable drugs, let's say weak acid and weak bases. And common ion effect we had seen now. It's upon how the ions is helping or doing the change in the solubility. So I hope you people understood the concept. Okay, if anything, please comment on the comment section. So we'll see in the next video. Bye bye.